Hello everyone and welcome back to another IB Math video about vectors. This is our second video in the vector series that we started in the previous video. And today we will be studying parallel vectors and unit vectors. You're going to see how vectors go in the same direction or how they can be scaled to a convenient vector of length 1, which is called a unit vector. So first we will start with parallel vectors. Imagine that you have here vector A, which is 4, 3. If we calculate the magnitude of this vector A as we learned in the previous lesson, it will be 5, which is under the square root 4 squared plus 3 squared, and that will be 5. Now, what happens if we multiply this vector A here by any non-zero constant number, like let's say, for example, 2. Here, when we multiply vector A by 2, then we multiply these by 2, so we have 8 and 6. If we also calculate the magnitude of this vector 2A, then we will get 10 by using the same magnitude formula. So notice that here, since we multiplied vector A by 2, even the magnitude got multiplied by the same number 2. And more importantly, these two vectors are parallel. So we can picture it like this. Here we have vector A, which is, as you see, 4, 3, as we have here 4, 3. Then vector 2A would be like this, 8 on x and 6 on y, as we have here. So as you see, they are parallel. You can imagine like they are two trains heading in the same direction, but one of them is twice as long as the other. Now here, what happens if we multiplied by -2 instead of 2, for example? First, the vector would be here instead of 8, 6. Since we multiplied these by -2, we have -8 and -6. If we also calculate the magnitude, it will be +10. The magnitude here would be like this, -8 squared plus -6 squared, which will be +10. So now, when we draw this vector here, -8, -6 with these, it will be like this. We start from here. So as you see, it's a vector of length also 10, but it will be the opposite direction of 2a's, just like parallel to them, but it will be the opposite direction since we multiplied by a negative number. So now here, from these examples, we conclude that when we multiply any vector A by a non-zero number, we get vectors that are parallel to the original one. So here, if vectors A and B are parallel, then one of them is a scalar multiple of the other. So when we multiply vector B by a number k, we get a new vector A that's parallel to the original. And also, the magnitude of A will be k times the magnitude of B. K here is in the absolute value. So like this, since we multiplied by 2, both of these are twice as A in terms of length. Now let's look at a 3D vector here. Here we have two vectors. Now, are these two vectors parallel? Like, can we find a number so that if we multiply this vector by that number, we get the other one here? Obviously, if we multiply the first vector by -3, then we get the next or second vector. So 2 by -3 will be -6, and so on for the other numbers, which means that these vectors are parallel, but the vector here is 3 times as long as the first vector here, but in the opposite direction because we have -3. Another example here, we have two vectors, but as you see, the components are not proportional, which means they are not parallel. Here, if we multiply vector 2 by 3, we would get 6. But if we multiply 3 by 3, we get 9, not 5. So that's why these are not parallel. Now let's move on to unit vectors. Imagine that you have a vector A, but you need another version of vector A parallel to A itself, but has a magnitude of 1, which is a convenient magnitude. That's what we call a unit vector. The unit vector is given by this. Here we have the notation for unit vector. It's 1 over the magnitude of A itself multiplied by the vector A. Now, unit vectors, the unit vector of A here is always parallel to the original vector. As we just explained, when we multiply A by a number, we get a new one parallel to A. But it has a convenient magnitude of 1 unit. Here we have an example. We need to find the unit vector. First, we need to calculate the magnitude of this, which will be under the square root, -3 squared plus 0 squared plus 4 squared, and that will be 5. Therefore now, the magnitude or the unit vector of A here will be 1 over 5 multiplied by vector A as it is. Now we can multiply 1 over 5 by each number inside, so we will have this vector 1 over 5 by -3 would be -3 over 5, and so on. If we calculate the magnitude of this unit vector, it would be exactly 1, just as we want. And also, this vector here is parallel to this A itself. Now, why are unit vectors important and convenient? Here, for example, imagine that we need to find a vector B, which has a length of 8 units. We need it to be in the direction of A or parallel to A. So we need to find a vector parallel to this but has a magnitude of exactly 8. So first we need to find the unit vector of this, which will be parallel to this and has a magnitude of 1. Then when we multiply it by 8, we will have the vector B that has a length of 8 times 1, which is 8. So first we will find the magnitude of A. The magnitude of A will be under the square root. We square here the component. Then we will get the square root of 21. And therefore now, the unit vector of A will be 1 over the magnitude of A as we learned here. Then we multiply by A. So now, this one here has a length or magnitude of 1. Therefore, to get B, we just multiply this by 8. We multiply the unit vector of A by 8, which will be now a magnitude of 8. Now, to simplify this vector here, first, 8 multiplied by 1 over square root of 21 can be written like this first. Then now, we multiply this number here by each number here. So, here we will have 8 over square root of 21 multiplied by -2 will be -16 over the same square root. Then here we have 8 times 1 will be 8, and then 8 times 4 will be 32 divided by the same square root. So this is here vector B. It's parallel to the unit vector of A itself, which is this, and also parallel to A itself, but it has a magnitude of 8.